Okay, ionic compounds. So ionic compounds are created when you have a metal cation and a non-metal anion bonding together. And it's not really bonding together in the fact that they are like joining hands or holding on to each other. All it is metals are cations, so they're positive, and non-metals are negative, and those two attract each other. Opposites attract, so it's just more of a magnetic connection rather than a welding or a fusing of those two together. And keep in mind that cations and anions can both be polyatomic ions as well. The only polyatomic ion that's positive, though, would be NH4. Okay, and then you guys should know the rest of your polyatomic ions, and almost all the rest, or all the rest, are nonmetals, or anions. Now, to figure out the charges of monatomic ions, so ions that only have one element in them, we can just look at what group they're in. So group 1A elements have +1, so that's the first row all the way on the left-hand side of the periodic table. Group 2A +2, 3, 3, 4, 4, 5, and then once we get over to this side, that's where the stair step comes in, and so we're going to end up having both of them on there. But at group 5, we would have -3 nonmetals, +3 and +5 metals, and then 6 would be -2, 7 would be -1. And of course, with the D block, it's hard to predict. Those are the ones you just have to know, and we use the Roman numerals to mark which is which. So if you think of the electron configuration as we're moving from left to right in the D block, when you start out at the first element, like if we look at scandium, for example, that would have a D1 configuration, and then the next one over, which would be titanium, would have D2, then vanadium with D3, so on and so forth. However, when cations lose electrons, they lose it from their outer row before they start losing them from the D sublevel. So vanadium, for example, if we follow the Aufbau principle, we add the electrons in, the last electron you would add in for vanadium would be the 3d3 electron. The one before it would be titanium with 3d2, the one after it would be 3d4. And so the thought might be, all right, so if vanadium loses an electron, it's going to lose this guy right here and become a 3d2. But that's not the case, because this is in the energy level 4, which means these two are the valence electrons. They're the ones on the outside. These are core electrons. They're still on the inner sanctum of the electron cloud. So it is going to lose these two right here, and it loses those two, and then it starts losing from the 3d. And so we can't really predict the stability. Like with sodium, we know that sodium is going to become Na+, because it has that single 3s1 electron that it's going to lose. And once it loses that, it becomes positive, it meets the octet rule. But with metals, well, we don't know what makes vanadium stable. Is it stable when it loses those two? Is it stable when it loses those two and one of those? We can't really predict that. Iron, for example. So iron, its valence configuration, or its last configuration, would be 4s2, 3d6. So if it loses those two electrons right there, it becomes iron 2. If it loses one of its Ds as well, then it becomes iron 3. And both of those will form. Even though these aren't necessarily meeting the octet rule for that particular atom, due to the organization of those electrons, it is stable in either one of those forms. It just depends on who it's reacting with as to whether it'll make 2+ or 3+. Basic take-home message: know thy Roman numerals. So you can go ahead and read both of these. It's just quick definitions. Remember, an ionic bond really isn't a fusing of atoms together. Instead, it's just an electrostatic attraction of opposite charges. And that first definition is just pointing out one of the ways they can form is if you've got sodium metal, it transfers its one electron over to chlorine because it wants to get rid of one, chlorine wants to gain one. When that happens, chlorine becomes chloride with a negative charge, sodium becomes sodium cation with a positive charge, and then as a result of that transfer, this positive, that negative attract each other, and we get sodium chloride. So the bonding is just once those ions are formed, then they suck together because of the opposite charges. But it's not just electrostatic attraction that holds these guys together. It is electrostatic attraction, and it is powerful, powerful thing. As a result, these bonds are very, very strong and require lots of energy to melt or vaporize the solids. So, for example, water, which is covalently bonded, it melts at 0 degrees Celsius and boils at 100 degrees Celsius. Sodium chloride, an ionic bonded compound, it melts at 108 degrees Celsius, much, much higher due to its ionic bonds, 800 times higher than water. And the reason is sodium chloride isn't really just sodium and chlorine together. Instead, if we were to zoom in and look at a salt crystal, what you'd see is sodium bonded to chlorine, and that chlorine is bonded to a sodium, and another sodium, and another sodium, which is bonded to chlorines, and sodiums and chlorines. And this can go on for a very, very long time until we get an actual salt crystal. So all of these positives, so the positive sodium is attracting all of these chlorines, and this negative chlorine is attracting the positive of all these sodiums, and so they form what's called a crystal lattice structure. We just call it NaCl, NaCl because they always exist in a 1-to-1 ratio, so we simplify it. So when something melts or boils, what's happening is the bonds between the individual molecules start to sever and they slide around past each other. So if we think about what makes something a liquid or a solid, it's because the molecules are moving around with respect to each other. So if we melt something, we have to break all of those bonds in there. So the crystal lattice structure of an ionic bond holds them all together, so it's like cement gluing every single one to the other guys, and it's going to be really, really difficult to melt or vaporize them. So what we see here, delta H, that's a measurement of energy we'll talk about pretty in depth later on. Lattice, so the energy in order to break the lattice for sodium chloride is 788 kilojoules per mole of sodium chloride. So this would be the energy required to break 1 mole of sodium chloride into 1 mole of sodium cations and 1 mole of chloride ions. That's a lot of energy. Okay, that's the energy to pull all of those guys completely separate so that they're now gaseous. Looky, looky, it's Coulomb's law. Coulomb's law can also be used to predict the relative melting points of ionic solids. So if we think of sodium and chloride as just a positive and a negative charge that are separated by some distance, we can look at Coulomb's law and know that as the distance increases, the force is going to decrease. So the bigger the cation and the anion, it's going to mean it's going to have a lower melting point. So if they're farther apart, that means less force holding them together, so it's easy to separate them into their individual parts. But as the quantity of the charge increases, the force will increase. And if the force increases, that means the melting point will increase. It'll take more force to pull them apart into their gaseous ions. And these would be the charge of a single ion. So something like chlorine versus sulfur. So chlorine forms a -1 charge, sulfur forms a -2 charge. So a compound then formed with sulfur is going to have a higher Q and therefore a higher force. Same thing goes for the cation. Sodium would be +1, and we would have something like magnesium with +2. And so something formed from magnesium and sulfur is going to have a higher melting point than something formed from things that only have a +1 charge in either. Of course, the distance would also play a role. But since all 4 of these are in the same row, they're going to have relatively the same distance between their nuclei, with some respect to the change because of cations and the effective nuclear charge. But something formed with a +2 -2 like magnesium sulfide is going to have a higher melting point than something like sodium chloride that has a +1 and a -1. So think about that, think about Coulomb's law, and see if you can answer these 3, then resume the video. So which compound from each of these sets has the greatest melting point, and why? Alright, so with this first one right here, lithium fluoride versus lithium iodide, they all have the same charge, +1, -1, +1, -1. However, fluorine is smaller than iodide, and since it's smaller, it's going to have a greater melting point because those radiuses are going to be closer together, and as radius or distance goes down, force goes up, so it's going to take more energy to melt those guys. With the magnesium chloride versus magnesium oxide, remember, we're looking at the charge of a single atom, and so this would be 2 plus and -1, so 2 plus times -1 would equal 2, and then if we have 2 times 2, well, that equals 4, and so this guy right here is going to have a higher melting point. Since the Q's are higher, you're going to have more force. And this last one might have been a little bit challenging because we're looking at distances and charges, but charges always play a better role. So when we're comparing two that, well, they've got slightly different sizes, but this guy right here has a much higher charge, then the much higher charge plays a greater role in the determination of the melting point. So always look at the charge first, then at the size. All right, so here's two models, and it says which of the following metal fluorides would have the highest melting point. Well, we don't see any charges on there. So how are we supposed to know if those are +1 or -1 and all of that? Well, it tells us in the question. It says these are metal fluorides. So that means that all of the anions have to be -1. And we can look at both of these, and since both of them are fluorides, they're going to have fluoride in common, so we can assume that all of the red circles are going to be our fluorides with a -1 charge. But then what's the charge on the cation? Well, for that we've got to do a little bit of counting. So we have 1, 2, 3, 4, 5, 6 fluorides, so 6 negatives, and we have 1, 2, 3, 4, 5, 6 of the positive guys. So in order to get those to neutralize out, it means these must all be +1 as well. If there's only 3 cations for 6 anions, that would mean it would have to be a 2+ charge. We just got to do and look at the ratio. So then knowing that the charge is the same for both of those, so the Q values are the same for both of these ionic compounds, the highest melting point would have to be due to radius. So this guy right here would have a larger radius because we've got a larger cation than this one right here. So remember, as distance goes down, force goes up. If force goes up, melting point goes up. What that means then is that B is going to have the higher melting point. So we can see that ionic solids are held together by all sides. So three-dimensionally, they're held together by that electrostatic force. That's going to make them very, very tight and hard to melt. And other things that they're going to do is they're going to be very hard. So if you think of a salt crystal, it's pretty tough. It takes a lot of force to separate that. And they also have low volatility. Volatility is a fancy word for evaporation. So if you set a cup of water on the table and a cup of salt on the table, the water will eventually evaporate. The salt's just going to stay there. So even though they're hard, ionic solids are also very brittle, and it's because of that three-dimensional, very, very precise lined-up structure. So if you take an ionic solid and you slam it with a hammer, what you're going to do is you're going to knock this perfect alignment of positive, negative off course, and so you're going to have things like positives and negatives touching, and those will repel each other, and so then they end up cleaving along certain lines. This is why ionic solids tend to shatter rather than just bend or mold. So something like metals that are held together just by more of a flow of electrons, you can stretch those into wires, which is ductility, and you can kind of squish them around, which is malleability. Ionic compounds do not have that property, though. They tend to cleave and shatter. And the last property of ionic solids is their solubility in water. So water is what we call polar, and what that means is due to the unsharing of the electrons, the difference in electronegativity, the oxygen molecules in water have a slightly negative charge, and the hydrogens have a slightly positive charge. As a result, then, we've got the plus charges of the anions, or cations, and they're going to be surrounded by the water molecules, kind of pulling them apart. Same thing with the anions. They're going to get surrounded by the positives from the hydrogens, separating them from the plus and negatives of the ionic solid. This process is called hydration, and it's just a matter of the water molecules surrounding the anions and the cations so that they can't get back together and form that solid. When we reach saturation, we reach the point where we can't dissolve any more sodium chloride, it's because there's no longer enough water molecules to surround all the cations and anions and keep them separate, and so they start coming back together.